Okay, do we want to do introductions in the beginning or when I go to the who is the professor slide? Begin. Okay. So. Hey everyone. All right, let's get started. So first off, welcome. It's first of meeting once a week for CS 200. So this class is a little different, as you can tell. There's not really like a professor. So we'll be going over exactly like what this class is, what the expectations are, kind of what you're supposed to do. But first off, so this is a club run course. So just introduce team members that is running this course. So first off, I'm Devin. I'm a junior, and I guess I just like machine learning. That's why I'm here.
I'm Darren. I'm also a junior.
Yeah, I'm Julius. I'm co-president. Doing BMS, working with Kate Isango. Yeah.
My name's Curtis. I'm a junior as well. I like my dog.
I'm Sophia. I'm a junior as well, and I do communications for NC.
I'm Jennifer. I'm a sophomore, and I like NLP. I'm Darcy. I'm a sophomore. I like machine learning.
Me too. Is that it? Okay, sweet. So first off, just like, what is this course? Why are you here? So this is just the course description from the syllabus that we have on a Google Doc. Just really two key points here. So basically, over the course of like these weekly workshops that we'll be having, we're just going to be introducing like different machine learning topics. You can see we're talking about just most of this is going to focus on deep learning, which is using neural networks. We'll go into all that. So really, don't worry if like things don't make sense right now. Like this whole idea is just a really relaxed environment to like learn through things. So we'll be going over things like computer vision, general models, sequential models, and reinforcement learning. If you don't know what that means now, you will eventually. And just a note, this is a 1-credit pass-fail course. So kind of think of this as like your CS PDP. Like we're again just here, enjoy yourself, learn something, make a project. Yeah, so there is a project that will be at the class. Like the whole idea of having this class is try to get people working on things, get their hands dirty. So part of the pass-fail requirement is having a project. So at a certain point, once we go through like some workshops, we'll try to sit down, everyone like either form a group. You'll probably be welcome to work alone if you'd like on a project, but that is part of the pass-fail requirement. So just be aware of that. So let's take a look at the syllabus. I don't think that's actually a link. So u.mic.bu. So if you want to find the syllabus, this is our website. And then this is just the CS 200 syllabus. So again, this is just the description we went over. We have a Piazza, so feel free to like ask questions there if something doesn't make sense in lecture, or come up to us after this or any other following workshop. Just listing some things. Julius, if you want to describe what you are to this class.
Yeah, so I'm the course assistant. Basically, I'm grading you. Just kidding. So basically, I just take attendance, and you can't miss 3 classes as long as if they're unexcused absences, then that was the deal. But
like,
hopefully none of you will have that.
Yeah, just let us know. Like we can work through whatever.
Yeah, just email me like I'm going to or anything. Yeah. So questions, just
email Julius if you have an attendance question too. If you don't think you recorded or something. Yeah. So just format, we're meeting once a week. It'll be hour periods. We'll try not to go longer than that, but a lot of times we'll have like coding stuff at the end. So if you want to like stay longer and work with that, we're happy to stick around. So yeah, again, it's mostly gonna be either workshops, like will be the end of this presentation today. We'll be doing just like going through some machine learning topic. And towards the end of the semester, starting midway, we'll just have time dedicated just working on a project. Like we'll have like tables out, just pull out your laptop, almost like office hour type thing, just work on the project. So let's look at the schedule. So these are all the topics that we'll be going over. Today is just introduction, okay, what is this class, and then kind of just what is machine learning. And then next week we'll be going into neural networks more in depth, kind of get you like seeing the math, matrices, all that. So then moving in overall things, one cool thing is we'll be going over like a research paper and then converting that into actual code. So you can kind of see, okay, we have a paper, this is something cool, it's all hyped up, what is it actually? Now you can be able to like understand, okay, here's where to find the important information in the paper, and maybe code it up as well. And then you can see at the end we'll have a lot of like work on project time, where it's just, okay, we're just gonna work on the project and dig into whatever areas of this machine learning that you want. Yeah. So, and again, just like who this course is for. So, we are just meeting once a week. There's no lab, there's no discussion. So obviously we can't go in as depth as something like 542, which is the actual machine learning course in CS. But this course is really good if you're interested in machine learning or deep learning and you want to like understand it better. May not have a strong background. Maybe you think a 500 level class isn't too up your alley at this point. But this is like a good time to explore and see what you like, what you don't like. And then this is also really good if you want to actually like make something. So again, like the whole idea of this class is to like make something, have something that you might be able to put on your resume, or leave it up on GitHub as a cool project by the end of this class. And then just talk with other people, learn a lot. So then just a note again, how this course is run. So we introduce all ourselves in the beginning. So we'll actually be the ones that are kind of like the professor. This is a club-run course. I don't really think there's any other BU, so this is kind of a trial in this regard. Professor Sanka, who does teach 542 and does a lot of cool deep learning research, she been helping out with this project. She is listed on the syllabus, but I would say probably don't reach out to her directly about this class because she's not really actively involved in terms of like day-to-day. Yes, sir.
So that was my, what's
Yeah.
her involvement? Because when I signed up
Yeah.
for this on Student Link, it said she is
Yeah,
the
that's
professor
under
of
her
the
name.
course, and it says her-
Exactly.
she's
Like,
the professor of the course.
yeah,
But
it's
she's
like
not actually involved with the
she won't be like in here giving lectures, like.
What will she be doing?
So she's really just like helping us out, giving us feedback on things, seeing that we're getting like salient points for machine learning, things like that. So that's a deal breaker. Sorry. But yeah. So yeah, we'll be the ones just kind of like giving the lectures, giving the presentations. So this is again just like a really relaxed class. Like we work on a project, learn things together. Yeah. Any questions on that? Like, good. Okay. So then just talking about grading. So I think Julius mentioned earlier, it's like attendance and completing a project. So you have like 3 freebies, just like completely unexcused. It's like don't show up, so use that whenever. If you do let us know in advance, then we can work with some wiggle room there. Obviously, don't exploit this system. Otherwise, we will have to like fail you a little bit, you know. And we complete a project, so that's also part of it. So taking this class is really just showing up and doing a project. Yeah, and again, the project, you might, if you're not sure of things, and you may bite off too much to chew, then you might not be able to like finish this project. So don't worry really about like completing the project. There will be some leeway in that way. Of course, we'll try to like talk through all this. Make sure you are doing a project that you can actually like get some meaningful work done on it. Okay, so that's like all the logistical stuff, kind of like what this class is, how it's being graded. Are there any questions for now on that stuff? You good? All right, sweet. So just going into a little introduction to machine learning. So, like, what is machine learning? Like, you haven't heard anything. Why is this, and what is this different from your standard like CS 112 or something, putting in algorithms and getting some feedback from the computer? Well, in this regard, machine learning is a field of study that gives computers the capability to learn without being explicitly programmed. So problems like learning to recognize a face. You aren't going to be able to write a hard-coded algorithm and be able to actually understand that well enough to put like literal rules, if-else statements in order to like find a person's face, what makes them different. So you need to learn from data in order to do that. So the whole idea with machine learning is that we learn from the data itself. So let's say we start with like some data. This is a really simple example, but it will illustrate our point. We have some input here, according to some real world value, and then that's probably a predictor for this y value here. And we can see here this follows your linear trend. Sure, there's some noise, but that's expected in real-world data. And this is our full data set here, and we can see it all clean and nice. So let's say we want to model this data. We want to learn from it. What can we do? Well, first we need to make an assumption about it, and that could just be that it's linear, that it's going to follow the shape of a line. So it would literally be our model, the equation of a line. You'd have your y equals mx plus b, b just being your y-intercept, m being its slope, something you've probably seen since middle school. And that is a model itself, and this is linear regression, and it is still used, and it works well, and it would do very well on this data here, being that it's a toy data set. And for sake of notation, moving into machine learning, parameters are usually denoted by theta. So in this case, theta 0, theta 1, each corresponding to y-intercept or slope. Once we get into matrices, as we go next week, you will end up with a matrix of just theta, just being your weight value. We'll get into that more. And then you still have your input, just being x. That will eventually be a vector as we go forward into neural networks. But for now, just think your standard line. And then f hat, that's just being our predictive model. So now we have this definition kind of what learning is. We're trying to approximate some unknown function f based on some data. We use this data to approximate that function. Like in the real world, there is some process out there that is generating this data. We want to approximate that function, that process that is actually generating this data. But that actual process is going to be really noisy. Like the real world is so complex, and so such like minute details have like such a chaotic effect on things that we can't really model that exactly, so we make assumptions on that data. So before we had all this noise in this data, that's just coming from some real world interference or whatever. And we're assuming that it's linear, and for our case, that's going to do well enough on maybe predicting some task. It's going to give us some accuracy that works well enough for our purpose. So we have this data, and then we're going to have this model just being a line, and that's going to be our predictive value, and that's going to be our model that is approximating that ideal function f. And this function is just going to map some input to some output. And again, that's going to be our model with our parameters that are theta. Yeah. So now we kind of get to the question of how do we know what these parameters should be? Like our data isn't going to be that clean. We can't like eyeball it or any way. So how the hell do we like actually set these parameters? We'll probably have to start at like some random point and adjust to those values such that they actually are going to fit our data. So also, maybe the data isn't going to be linear. Maybe it's going to be all wavy or whatever. Maybe there's going to be so many dimensions that you'll never be able to get a good, accurate plot on 2 dimensions here. So maybe we need a model that's not just a linear model. Maybe we need something more complex. And that's where kind of neural networks come into. When we need to do more complex modeling, neural network gives us that wiggle room in order to do that. So these 2 questions right here are really the core of what we'll be like digging into in this like workshop series. Like how do we set these parameters? What optimization techniques do we use? How do we know what assumptions to make? Maybe how do we know like what model to use? Maybe not a linear model, maybe a neural network. But there's like tons of different types of neural networks. So which ones do we choose? So we'll be trying to build like the intuition of what we want to use. Maybe for like language, that's a different model than something for images. So this is what we'll be digging into more.
Okay, leading from there, we're going to talk about the intro to deep learning. So what is deep learning? Well, the overall theme, most of you know artificial intelligence. It's made up of lots of machine learning, deep learning. They all work together to create AI. Then a subset AI is machine learning. And then as you go deeper, there's a branch of deep learning. And so machine learning is the subtopic or the overarching idea of deep learning. And so we're going to go talk about why deep learning is a subset of machine learning. So deep learning learns from data using a class of functions known as a neural network. So you get an input, x, feed it through the neural network, and it is mapped out to an output, which is y. So you can think of it as feeding it a function with an argument, which will just give you an output, y in this case. Applications of deep learning, there's almost an infinite use of it. You see it everywhere. You see it every day. A huge example is computer vision. specifically in Tesla. And so Tesla just recognizing items on a street that involves a car, street lights, pedestrians, bicyclists, the road for path planning, where to go in the future, and perception, where it is actually on the road. So computer vision, it's always getting better. Tesla's feeding its data it records every day to the cloud. So it's always improving upon that. Text generation, some scientists created an algorithm to create a similar Shakespeare piece based off past data it had of Shakespeare. Image recognition, going back to computer vision. What's in the picture? A cat, a face, a dog. And an interesting branch of this is Facebook's photo tagging. Is if there's a picture of you on Facebook, it'll tag you based off your past data you gave Facebook. So it's kind of creepy in a sense that Facebook knows what you look like, and so it can tag you that easily. And another one is an Apple Watch or smartwatches. There's a new feature they have where you can just type a word out letter by letter, and it'll know what letter you drew on it just based off past data sets. And that could be used based off the MNIST data set, if you guys are familiar with that. That's a similar application of that. And many, many more applications of deep learning. It's used in almost everything. And so, what have you guys heard about deep learning / applications?
AlphaStar.
Yeah.
AlphaStar?
The facial recognition, image processing.
Yeah.
Mhm.
I know it has a lot of monetary applications.
Yeah, like a lot of trading, like finance stuff, trying to
Mhm.
game that stock market.
And even healthcare?
No, Palantir.
Oh, okay.
Fastest way to complete a Mario level.
Yeah. Saw that YouTube video?
Yeah.
Do you have one?
Making ads, targeting ads.
Yeah.
And another big one, cybersecurity, recognizing patterns. Hackers are trying to get into patterns. Hackers are trying to get into frameworks, websites, all of those. Yeah. So biological neuron versus artificial neuron in a neural network. So as you see, the biological one has a nucleus and axon connecting it to other neurons. So if you look at the artificial one used in neural nets, you have the cell body, and then the WX, X2, the weights, are the ones connecting the other layers to each other. So one artificial neuron to the other are connected by weights.
Yeah. So, kind of just a quick preview of what this is going to end up looking like. So we're going to end up like stacking these individual units into these big networks, and you may end up with something like thousands, tens of thousands. I'm sure some really like OpenAI stuff has been like hundreds of millions parameters. GP2. So it's building this massive network of these neurons, and so our analogous mathematical like model of this actual biological neuron is what you see here on the right. And so as Darren described, you have this nucleus that's taking in all these values from these previous neurons that we're feeding in, and it was going in and it's informing what's going to then be sent out in the axon here into other neurons. So that's that network being built. You have this input from other neurons going out into other neurons until finally you get like some sort of completion there. And so how we model this like mathematically and what these neural networks will actually end up looking like is having these inputs into this cell body by a weighted sum. So it's going to take in from one neuron, maybe this is x0, that's going to be that output of this previous neuron here. And we're going to multiply that by some weight value. So it's like how important is that input for this, what this specific neuron is doing. Now we don't know exactly like what any specific neuron is in like a massive network, what exactly that neuron is doing or what exactly that thing is learning. That's actually a whole field of research, like interpretable ML, interpretable neural networks. How do we actually understand what this is? But for this purpose, it's like you're taking in these values and you're weighting them by some value. And then this neuron is only going to give one output. So it needs to decide, okay, what is that value? So it's going to do that by aggregating all those values going in together, and that's going to be that sum value right there. And you do have that bias value just for mathematical, like it's just like shifting that line. It's easier to move that function around. But just think of it as aggregating all of these inputs in together, and then it's going to feed it into this function. If you remember from like psychology or like biology or whatever, a neuron has like an all or none response, right? It's either going to send a value out or it's going to do nothing. So we kind of mirror that. Again, this is very like iffy analogy between like actual biology and what we do in neural networks. But we model that by doing a function around that. And that is necessary such that you aren't just stacking lines on top of each other, and then that would just reduce into a line. So by stacking these functions as well, you get a lot of like wiggles basically, and we'll go into that more on the networks workshop. But for right now, just imagine like you're inputting all these values, you're aggregating them together, feeding it through some function, and then you get one output value. And that is for one of these units. And then when we build a neural network, it's a bunch of these units all together. And by having all of these values together mixed with all of these weighted values, all these functions stacked on top of each other, you get a really complex function here. If you like wanted to like write that out by hand, you'd have something like ridiculous. So it gives us a lot of wiggle room, and we can model much like more complex data, like image data, video data even, and that's all encoded in these weights of a neural network. And then just some notes on the notation here. So you have the input layer. That would be the actual values coming in from that training example. So that could be the literal pixel values of an image that are being fed in. And then the output layer, it's kind of arbitrary where you set that output layer to be. If it's 4 values, it could be 1 value. If you're outputting like a probability, like let's say you're putting in a cat and you want the probability that this is a dog, that should probably be pretty low, but between 0 and 1, that would be your probability. Or you could have multiple out there. Maybe that's like 4 classes. It could be like a cat, dog, or like 2 other animals. And then like the largest value outputted on that indice indicates that that's that animal. So it's outputting a value there, and how you interpret that is kind of up to you and how you're going to train this model. But we'll get into that more again in the next workshop. Yes.
So quick question about the sort of the analogy earlier with like the all or nothing. So is it when they all receive enough like weights coming in, it fires off, or does it always output something?
Yeah. You could have something. So it's not going to follow that exactly. You could have a function that being like a piecewise function, like if it's greater than this, then maybe I'll put some value. But you're going to run into problems there in how we train. So it's usually something like a S-curve value where you make between like 0 or 1 or like -1 and 1, and then it's going to output along those lines and get a continuous value. So it will probably always output something. Some of them might learn to output something like really close to 0, so it like kind of doesn't matter. Yeah. Yeah, feel free to like stop for questions at any time. Okay. So going to steps to train a neural network. So the first step is forward propagation. Quickly, so you see the whole like 3 steps here. We have forward propagation. We compute the cost. And then we update it. So those are the 3 steps you have into training a neural network. Except you do those 3 steps like thousands, tens of thousands, millions of times. And then you end up getting good values. But going back to forward propagation here, this is where we start, and it starts from just pushing an example through the model. Did you want to?
Yeah. So push an example through the model. A good example of this is calculating the price of a house. So 3 inputs, 3 dimensions, number of bedrooms, number of bathrooms, and square feet. So simple, probably not accurate with only 3 inputs, but just an example. So you have 3 inputs, a bunch of hidden layers, and then the output, which Devin said, is calculating the price of a house. And so, do you want to explain the hidden layers?
Yeah, so remember how we talked about those units, those cell bodies, it's aggregating all those values in a sum, and then applying a function. So the reason you're stacking them is just to add, you're allowing for more complexity to take form there. You're building like a more complex function. So you'll be able to learn like a different curve in some area and like a plane of data, if you can kind of imagine that. So it basically allows you to learn just more complexity. So in this case, for like price of house, it's probably too much to have like a lot of hidden layers or something. Like it's kind of just, this is for the sake of example. But when you're doing things like image data, it's much more useful to have hidden layers stacked on top of each other. People have done like hundreds of layers stacked on top of each other and such. So yeah, so that's kind of FOIA propagation.
Can you give an example of what you mean by when you say like it learns like some more complexity?
Yeah. So if we go back all the way to this like data example right here, and then we have this line, right? That's kind of our model. So if you even look back here on the cell body, what this value is, if there was only one input there, it would be like that linear value here, like that mx plus b, the w being the slope, b bias. So that's probably your simplest case right here. But let's say this was a curved like data, right? You wouldn't be able to do that with just a line. You wouldn't be able to like separate it or anything with just a line. You need a more complex function. You need something to be able to curve, twist, bend, and if we're dealing with like much higher dimensional space, it's gonna need to like flip on top of like just really weird stuff. So by stacking these things on top of each other, you're gonna be able to have like much more complex things than like a line. Is that
Yeah.
okay? Great.
Cool.
So you get this output from this example of, let's say you get a price of a house. So then moving in, okay, we get a price of a house, but again, we're probably starting in a place that's just random values and all those weight values, so it's not going to do well at all. So how are we going to get to that stage where we update it? The very first step to like update is we need to know how good or how bad this model is doing, and we call that the cost. We say, okay, this model right here, this is our approximation, right? It's that line. But that point is that far away from the predicted value. It's like that actual value minus that predicted value. That's like your error right there. So if you did that for all those points along those lines, you'd end up in an equation like this. You would have that predicted value minus that actual value summed up for all those data points, being m being the number of data points, I being that example. And then you sum that all together. Then that's your like total cost value for how good this model is doing on that data. So again, it all ties back to this idea that we're actually learning from the data itself. That we're using the data to say, okay, this is how good this model is doing at approximating that data. So it really comes into play here when we talk about computing the cost. We'll go more into cost functions. This would be an example for something like a regression problem using a price of house. More, again, NeuroLogix, different problems will require different cost functions. So you'll see a lot of different cost functions. So just taking into account right now, okay, it's telling you how good or how bad the model is doing. And now based on that, we'll be able to make an update actually. So this is when you need like calculus here when you have the derivative. Because what we want to do is we want this cost to be as low as possible. So if you plot this cost, you could end up with something without hills and values. But that's going to be really hard to think through. So imagine just like a parabola for now. That lowest value that you could possibly get is right there, that minima, right? Now in calculus for like an x squared, you could just do that derivative, set that equal to 0, and you know exactly where that value would be. But when we're dealing with all this dimensional stuff, when we're complexifying, we're having a really complex function, it's going to be really difficult to do that. So what we do is we do an iterative process. We're going to say, okay, we're going to start at this one point, that value being, that blue ball being, let's say, what this cost just told us, where we're at. We want this cost to be less, so what do? And those y values are using the model. It's using that line. So there's those parameters associated with it. So we'll know by the derivative, that being that slope at that point, so you know which way is up, but we want to go down. So we just go in like the opposite direction, subtract instead of plus. And then we take a small step. And then we're slightly better off after using this data example. So again, we're using the data to learn here. We're going to take that step towards that minima. And this small example doesn't really generalize to all like the really weird hyperplane kind of stuff. But the actual process of doing this iterative update based on that slope, that derivative, that gradient, we'll also go into this more, will end up taking us to that local minima, and we'll be able to find that smallest value for that cost function. So that's what we're doing there to make that update. So those are the 3 steps that we'll be doing, and that's just like an example to see kind of why it's called backward propagation, or also you'll see backprop a lot. It's going backwards through that network. If you recall from calculus, you have the chain rule. So again, it's all these nested functions. It's just going to go backwards through that like nest. Any questions here? We will go into this more, but happy to answer any.
Can you go back one slide? Wait, one more, sorry. The one with the line. Which one is the guess? Are the dots the guesses or the line the guess?
The line is the guess.
Okay, that makes
Yeah.
sense.
Exactly. We're trying to find like the parameters that are that line.
Yeah.
Like the line, slope, and bias. Yeah. Okay. So those are the 3 steps. Forward prop, compute the cost, back prop, make that update. So those are 3 costs. Now note on actually how we divide up our data, such that you'll know that your model is actually going to be able to generalize into like real world data and actually be useful. Like you can imagine on this data, if you had a function that literally went through every single line really close together, that would be known as overfitting. But we don't want that, so we use a simpler model or we do different techniques. But for now, just kind of think in terms of almost like practicality. This is what you'll actually be doing probably if you're doing a project. So you have all your data. You take this data and you're going to divide it into trained data. You want this to be like the biggest portion of the data that you're using. And this is what you'll actually be training your model on. And you'll have a test data set, which will be the end of the day. This is like a really pure data set that you don't touch until the very, very end. And you'll also have a development data set. So the training data set is to tune all these little parameters that are all throughout this neural network to get them to actually learn something. Then this development data set is maybe there's some hyperparameters that you're working with here that we'll also go into more if you're not familiar. That might be something like the learning rate. There's some other things there. But that's going to help you like tune things that are on a higher level than just those low-level weights. And you don't want to touch that test data set until the very, very end because that's like kind of your example of real-world data. So how you do on that will be a really good indicator for how you do in the real world. So that's pretty much it for today. Are there any questions?
Just with the last thing you said.
Yes.
You said the data trains things on a higher level, like or
Yes.
than the normal. Like, what is that?
Yes. All right. So in this cell body, you have that W. I think that's my phone. Okay. So you have all those W's right there going on the input, and those are like your weights. Those are your values that you're trying to learn. And now you have all these, and you have a ton of those. You have all these connections, so you have a ton of those weight values. So that's like the low level that you're learning. You're learning all these details to learn and approximate this data. But on the high level, there's going to be different steps or different like values you're using to learn it. So let's say this gradient step right here. So how far you step, that would be an example of like a hyperparameter, and that would be called your learning rate. Why don't you step like all the way down? Why don't you step like just a little bit? That's kind of something that you have to figure out as you go. So you'd have to train all those little weights, all those low level weights, before you can actually see how that like upper level thing did, being that hyperparameter. And if you go and test on your test data set, then that's kind of poisoning the test data. You already like touched it, you already used it, and now you're learning from that data. We don't want to learn from that test data. We only want to learn from that trained data, and we will end up kind of learning from the development data. Yeah.
I'm still a little confused about the graph with
Yes.
the parabola. Is that the weights for those W's earlier, or how's the blue dot on it shifting around?
Yeah, so that is the y-axis being that cost. So that would be the result of that like summation here. But it's with respect to the parameters. So your parameters are going to determine, like in this case, that line. So it's going to determine, okay, how well it's approximating that data. So we want to update those weights. So it's the cost with respect to the weights. And we're going to use that to make the update. So then we update those weights. And that's kind of that learning procedure, how it goes. We update the weights.
The cost is kind of like how wrong you are,
So,
like how wrong your model is.
yeah.
Okay.
So it's just minimizing how wrong you are.
Yeah, so trying to get to the
Yeah,
truth of that.
exactly.
So is that the formula of like sort of building the regression that's being shown right here? Is that the idea?
Yes. So this is building. This isn't that line. That would be the weights and stuff all together. This will build this line. So there's the cost curve kind of and like the model line.
Yeah.
So the model is like that line in that example of data we've been seeing. And then this is just from this cost here. Yeah.
Oh, is that all that done in the hidden layer? Like the adjusting the weights and all that?
Yeah, so you'd see how like you have all those arrows going through.
Yeah.
It's like those would go through all those hidden layers too if there was like a ton of them stacked up. So it's like background.
This is just kind of like a question in general. So if you go back to the neural network slide, or 23, or yeah, that one's fine. Would there ever be a reason to not have fully connected layers?
Maybe. You could do something like there's like evolutionary ways of building a neural network, so you only do like certain connections.
Also, convolutional neural networks. Those are
Yeah.
used for computer vision because when you have an image with like so many pixels, like it's computationally like expensive to do fully connected.
There's also a bunch of models that have skip layers or something. I don't know what, like they're used to train
Like
certain layers better or something, but they're not used a lot.
Fun fact.
They exist.
So when we do this paper implementation, it'll be using skip layers, exactly, and you'll kind of see like, okay, why these might do better. So we'll be playing around with like different architectures, kind of. The ones we've been seeing so far would be referred to as just your standard feed-forward neural network or a fully connected network, or like multi-layer percept. Like there's just a lot of names. Like just this is your standard neural network. Like we'll know what you mean if you say that.
Given that we only have, like, it's more of a general question, but given that it's like 1 hour a week, like,
Yeah.
could you guys send out some, like, or do you guys have, like, materials that, like, you would recommend, like, on
Yeah,
our
we're
resources?
planning on sending out everyone associated. Didn't for this one just because.
Yeah, so if everybody is registered on Piazza, I'll be sending out
Yes, it's on the syllabus.
regular emails on that. There's an email list that you can join. About that.
Also asked if we had a Piazza code. We'll try to send an email with that. It's also in the syllabus if you want to do that yourself. But yeah, we'll try to send an email with all this stuff. Like if you have like suggestions for us, like let us know. Like we're totally flexible to do things. Again, this is supposed to just be like us learning together, having a good time. And we'll do our best to come and give you resources that you need. Yeah. And we'll have pizza like every time. So. Yeah, so that's pretty much it. Like, you're free to go. Feel free to stick around, talk, whatever. Yeah, thanks.